Okay. So the natural log function. So on Friday we talked about the natural log function being defined as natural log of x is equal to the integral 1 over x of 1 over t dt when x is greater than 0. And I showed you that essentially, that is not what I wanted. It was the area under this graph. It was this bit. And that area represented the natural log of x. That is why up here, when we said the natural log of 1 is equal to 0, because if you put 1 into that integral, you don't have to write this down, you're going to get the integral from 1 to 1 of 1 over t dt. Right? And if it's point to point, you know that there is no value. There's no area under that curve. That's why it's 0. All right. So using this, if this is our f of x, and I talked about this on Friday as well, f prime of x is what? Sorry? Okay. 1 over x. Yeah. Of this function. So 1 over x. Therefore, the derivative of natural log of x is equal to 1 over x. Now, if I said replace the x with a u, which could be any function, and I said f prime of x, I guess that'd be u, f prime of u, sorry. Is going to be 1 over u times the derivative of whatever u was, so u prime. So then we get the definition of the derivative with respect to x of the natural log of u is u primed over u. That's what we're going to use mostly because you don't usually just have natural log of x. You have natural log of a big complex thing. I'll give you these formulas. I'll write them on the board just like those ones over there. But they're not too bad to memorize or to use because we use them so often. So now we're just going to run through a few examples, give you some practice questions, and then we'll move on to the next level. So first one. What is the derivative of the natural log of 2x? Use the second one here. U primed over u. So our u is 2x, what you're logging. What's the derivative of the 2x? 2. The 2's cancel and you get 1 over x. The derivative of the natural log of x squared plus 1. That's it. You just take whatever's in there, goes into the denominator. And then in the numerator, it's whatever that derivative is. So in this case, 2x. So derivative of x times the natural log of x. So what rule do I need to use here? Product rule, right? Because it's two functions being multiplied together. So product rule says derivative of the first function. What's the derivative of x? That's just 1 times the other function plus the derivative of the other function. What's the derivative of natural log of x? 1 over x times the first function, which is just x. What's x times 1 over x? 1. So my answer is just natural log of x plus 1. So derivative of the natural log of x cubed. So you have choices at this point. Okay. One way to do it would be to do what we've been doing. It would be the x cubed goes in the denominator. What's the derivative of x cubed? X squared. That cancels those, and you're left with 3 over x. That's one way, perfectly good. The other way is you could rewrite it as 3 natural log of x, because you're allowed to drop that exponent down. The derivative of a constant, constants we don't even worry, well, we don't, something we don't worry about them, but we can pull them out. So when I do the derivative, I just have 3 times, what's the derivative of natural log of x? 1 over x, which is the same as that. Okay? Usually when they get bigger and more complex, it's better to drop the exponent down. But something like this, it doesn't really matter. Okay? Oops. So what's the difference between this one and the one above it? Chain rule. Is that what you said? Yeah, that's exactly it. Because this 3 means it's natural log times natural log times natural log. You cannot drop the 3 down. You can drop it here because it's on the argument. But this is not. It's the whole thing. So you have to use chain rule, which says drop the 3 down times the inside derivative, which is, there you go. And the notation, you can leave it like that. That's perfectly fine. But the notation, just like the trig stuff, is this. You'd put the 2 on the natural log. I don't care if you write it like this, though. They mean the exact same thing. Let's make it x squared plus 1. So the derivative of the square root of the, the derivative of the natural log of the square root of x squared plus 1. Do we like square roots? No, we want exponents. So we're going to rewrite it. what can I do with the 1/2? You can bring it down because it's on the argument. And now it's a much easier derivative. I don't need to worry about the 1/2. So I can just put 1/2 out there. The derivative of the natural log of x squared over x of x squared plus 1 is something over x squared plus 1. What goes in the numerator? 2x. And then those 2's will cancel and you just get okay. So f of x is defined as the natural log of that gong show. I'm not going to derive that gong show. You could go 1 over all of this times the derivative of all that. But the derivative of all that, like I said before, is a product, a chain, and a quotient with a chain inside that quotient. That's going to be huge. But because it's a natural log, what can we do first? What did I? Okay. So the top 2 are being multiplied, so I can rewrite it as natural log of x plus, I'm going to drop the 2 down. The bottom is being divided, so I can subtract it off and change that to a power of 1/2 and drop it down. So now this is way easier to deal with. What's the derivative of natural log of x? 1 over x. So if I go, okay, f prime will be 1 over x plus the next bit. The 2 is a constant, so I can leave it there. What's the derivative of natural log of x squared plus 1? It's 2x over x squared plus 1. And then you do the same for the last one. So it'll be 6x squared over 2x cubed minus 1. I mean, you can clean it up a bit. And that's it. That's a pretty straightforward derivative once you've got it broken up. And this is why I said logs actually make your life easier. Because if you have a log, or you're going to see in a bit, when you do log it, you introduce one, you can rewrite it like this and you do each one separately. Now you can make a common denominator and put them all together, but just leave it like that. All right, on a test, leave it like that. We okay? Break it up, use u primed over u, and then that's it. So, page 325. Numbers. (41 to 59) odd. You're not going to have enough time to finish all of them in class, but that's okay. Right now, anyway. Up till this point, we have been given questions that are defined with a log in it. All right, our function is the natural log of all this stuff. But obviously, not all functions have logs in them. So this is something we could have done before. Y is equal to x minus 2 all squared over x cubed square root x squared plus 1. But like I've said before, or in the last 10 minutes, this would be a nightmare to do with chain quotient product, okay? It's going to get really big, really messy, lots of places to go wrong. So we can use logs to our advantage, all right? Because they allow us to break it up into individual derivatives. So what you do, just using the skills you learned in grade, 5, whenever you learn it, what you do to one side of the equation, you have to do to the other side of the equation. That includes if you log one side of the equation, you log the other side. And we're going to log both sides of the equation, natural log both sides of the equation. So this is going to become the natural log of y, the natural log of all this stuff. I'm going to get rid of the square root and write it as power of a half. All I did was put a log in front of both sides of the equation. Now I want to take the derivative. So start with the left side. What is the derivative of the natural log of y? It's 1 over y times y prime. Okay? Because we're deriving it with respect to x. So this is going to be y primed over y. The other side, before I derive it, I'm going to rewrite this. Okay, I'm going to break it up. So this is going to be 2 natural log x minus 2 minus 3 natural log of x. I'm going to put this all in brackets. Plus 1/2 natural log x squared plus 1. So I just broke up the right-hand side of it. I dropped that 2 down, got that minus because the bottom is being divided. Put in brackets. You don't have to put brackets if you know that. Just remember to flip the sign. And I dropped both exponents down to get this. Now I can derive this, which is way easier than doing this whole thing together. What's the derivative of this? One over x minus 2, right? Times the 2 in front. So it's going to be 2 over x minus 2. Minus natural log of x. The derivative of that is 1 over x. So it's just going to be 3 over x. And then next one's going to be subtracting 2 because that negative gets multiplied in. So it's minus 1 over 2. The derivative of x squared plus 1 is 2x over x squared plus 1. And then again, you can clean it up. I'll write it below, actually. Am I done? Whenever a teacher asks you that, you know it's no. But why am I not done? You go y primed over y. We're trying to get the derivative, y primed. So multiply the y up. Y times all of this stuff. What's y? It's that thing. Just put that in front. You don't have to clean it up. You don't have to do any of that. I'm not going to make you do any of that stuff. So it's x minus 2 squared over x cubed squared plus 1 to the half times all this stuff. Now that's a big, ugly derivative, but it wasn't that hard to get because we were able to break up this right-hand side. If you try to do that, well, you can, I'm not going to do it. Try to do it using quotient chain, all that to get this, it's going to be a nightmare. Okay? With a lot of places you can go wrong. So whenever you see, you can use this whenever you want. Whenever you have a function that is really gross and ugly, and if you don't want to use all those, you can log it and break it up. Okay? All right. Let's give you 2 questions to do. Page 326, numeros 89, and you can do 91 or 93. I don't care. Or both. I'll give you 10, 15 minutes. 11:10, we'll start integration, so you have 15 minutes.